definition to prove this limit here. So
That's easy. Yes.
Can we check if this one is books later?
It will be. Most likely it will be.
we want to eventually find some m value, so that any x passes this m value, then we'll have this symmetry. So let's just rewrite this in terms of the actual function. Now that's this absolute value of fx minus limit.
Once you finish that question, start coming there.
Sorry?
Once you finish the question, don't start from here. Okay, Jenny.
We're going to
Combine
delete
this
the previous
into
string.
Yes, yes, yes.
one function.
Delete the previous string. Edit the photos and roll out.
So I'm just adding all the absolute values in. Now, because this is the absolute value, and
We are really low on time.
plus
So,
it,
speed.
since also x squared plus 3, well x is 0, that's always going to be positive. Now,
Like, I
This-
allow the two years later to it, and we finish with like one, we're 1 question behind, cooking down.
is that it? We want to show
Actually, let me
that's
check for free rooms.
less than epsilon for some choice of limit m. Now, if we want to show that
We got bailed. Holy shit. Holy shit. Holy shit. Got bailed. Got bailed. It's free.
then what if we just use an intermediate value? Intermediate expression. This is
Take your time. Take your time. Don't let that spoil.
If you decrease the value of the denominator, then whatever the result is, it's going to be bigger, right? And so actually, if we just find some value so that this is less than epsilon, then, well, that's less than that, so that's going to be less than epsilon as well. Now, what we want is this. So we rewrite it like that. Now, now we know that
Thank you, Georgia. Go back. You can do it here now. You can do it here. He has a question.
Oh.
No, he has a question. He was asking.
I can laugh so
Wow, how come?
That's funny. Dynamic interaction.
Oh, sorry.
Oh, okay.
Yeah, that's
Get
just
the
an
audience in there. You're a real showman.
No, definitely. Thank you so much for your.
Sorry? Does it not allow you?
We just started new stream because we haven't really used that app. We just started new stream.
It's going to be more complicated.
Show me.
And if you can make it simple, well, why not?
You can, at least you edit the title. Right? I know. Wait, can you edit description?
You can. I already edited it. You just can't edit
The image. No, that's fine. Because I did it yesterday. I only did it after the stream. I don't think it's reasonable to do it in the stream. So it's fine. Yeah, no worries.
Wait, so am I able to?
Yep.
Yeah.
Yep. Just, okay. It's like pretend this is the screen and then, yeah, draw.
Okay.
Did you know that?
Alright.
Yes.
So like, you can scroll down.
Yes.
All right. At this distance?
Yeah, just.
Okay. Okay. So what we have up on the whiteboard, that's basically what's over there, except on the slides. And then yeah, that's the rest of that. Now question 3. Here we have a limit question. Now, is there a way to get like more paper on the
You
side?
can probably scroll like that.
Oh.
Yeah. Or you can zoom out if you want.
Yeah, just infinite space.
Okay.
Okay.
Okay, nice.
What?
What?
Use this instead maybe
Okay.
when you're drawing out. So.
So how does one use this? The- Should I just go back to that? Should I just go back to that?
You want to do that? But then how online? Wait. What was the issue?
Cause like this is just very hard to write with.
Your handwriting will get better.
Okay. How do I do backspace?
You just do Control Z.
Okay. Okay.
Just
Oh my gosh.
okay. Go back to the stream and then we're not changing. Just like have the have it on. Yeah.
Oh no, it's just the map.
Guys, very sorry we're bad with tech.
We're academics, not IT.
Okay. 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 So we want to solve this limit. Now, we see on the numerator and denominator we have an x squared term, and if we just split up the fraction, then that'll cancel out. And so we get
Do you wanna just move up a little bit, move up the page, can you move up?
No. Move the camera. You can just move it here, and it doesn't take up a billion of space.
That's outside this.
Just try to not write, like try write directly.
Okay, that's fine.
Try write directly.
on the slides.
Don't write any other. Just write.
I don't have space for that.
No, because otherwise you'll like the text is blocked.
No, trust me, it'll work.
Okay. All right. Okay, yeah, splitting up the fraction, we get this.
You can talk closer to that microphone.
Okay. All right, now this is gonna be
No, it's just super quiet. And say, was like super quiet, you say?
okay. So here you can see I've taken the 3 outside the limit. That's fine because it's a constant. Now we have to evaluate this limit here. We can see that this sine 2x squared over 2x squared oh, wait, sorry, this is the copy down the question wrong. This was to 0. And now the limit of this, we can take the 2 out. Right. Now the limit of sine x over x as x approaches 0, that's a known limit. And so we can treat this sine 2x squared over 2x squared as the same thing. Formally we can say like let u equals 2x squared or whatever. And then the limit is going to be the same. Okay. And so we have that. Does anyone have questions about that? No? Okay. Okay.
Oh, we don't. Okay, yeah, use this in this interchange.
Okay. All right. So therefore we have the limit is 5. Okay. Any questions? Okay. Properties of continuous functions. So a function is continuous at a point. Right, function is continuous at a point x equals a if it satisfies the following conditions. The value of the function at that point has to exist. The limit as x approaches that point of the function must exist. And that limit has to be equal to the value of the function at that point. Now, we also have the intermediate value theorem. Here, if we have a continuous function f on a closed interval from a to b, then if we have value z, which lies between fa and fb, then there's at least one real number in between there, in between a and b, where the value of the function is going to be equal to z. Right? Any questions about that? No? Okay. Can move on to this question then. Okay. So here we have this function from a to the reals, and it's defined by this equation over here. And now we want to find the maximal domain of this function. So we need to think about what might restrict the domain here. So with this natural log function, we know that whatever we input into the natural log, it has to be positive. Okay. If we just look at the denominator for now, we see that we have this cosine function, and the value of cos of anything, that's always going to be between -1 and 1, since we're dealing with real numbers. And so the lowest that the denominator can be is going to be 1. And now 1's greater than 0. So actually the only time that this bit will be negative is when the numerator is negative. This means that we want the numerator to be positive. Then okay, taking the natural log of both sides, get this. And so the domain, the maximal domain, is going to be from x goes to it's between, okay. So it's going to be from natural log of a half to infinity. Now these open brackets, because it's a greater than, and with infinity you always have an open bracket. Okay. Any questions about part A? All right. Okay. All right. Part B.
Okay. Slow down. Actually, okay. Okay, actually part B, I'm gonna write down here. So, now part B says, by considering the intermediate value theorem, explain carefully why fc equals 1 for some c in the domain A. Okay, now we're gonna use the intermediate value theorem. So we want to find some A and B where and these A and B have to be in our domain. And so our domain, remember, is natural log of a half to infinity. And if you think about it, since a half is less than 1, then this natural log of a half, that's going to be less than 0. So 0 is in our domain. So we're going to guess that A is 0. Now, I might have to write on the right because of seeing that. Okay. Now if we substitute that into the function, we get sorry. Okay. And then if we evaluate that, I'm just gonna do these steps a bit quickly here. Okay. Now that's less than 1. And here, I'm just gonna guess that v equals 1. And what we want to find is that fb is greater than 1. And this is one where you can't really evaluate it nicely. I'm just going to say, if you use the calculator on this, you get, it's roughly 1 point something. And so that's going to be greater than 1. And now, by the intermediate value theorem, because we have some A in the domain and some B in the domain, where FA and FB, we have 1 is lower than 1, 1 is higher than 1. then we definitely have some value c in between them, where fc is 1. And because a and b are both in our domain, A, then c is also in our domain. So here we have the result that fc equals 1 for some c in A. Any questions? Okay. All right. These slides, they're just the same solution. Here they have negative ln instead. That's just another way to write it. And this is the same thing, just on the slides. Okay. Differentiable functions. So if this this is the definition for the derivative. If this limit exists, then the function f is differentiable at that point A. And also, if it is differentiable at A, then it must also be continuous at A. This is not true the other way around, though. Continuity does not imply differentiability, meaning if you know something's continuous, you can't just say it's differentiable as well. Okay. Now, here we have a question. Consider this function defined by these piecewise equations. Given that h is differentiable at x is 1, find the values of a and b. Okay. So h is differentiable by what we just went through. If some function's differentiable, then it's continuous at that point. So h is both differentiable and continuous at x equals 1. Now, what does that mean? That means that if we substitute in x equals 1, then we should get the same values in each of these equations. And now this is for continuity. Now simplifying this, we have that. And so we have this is one equation. Now this function's also differentiable at that point. So we need to find the derivatives and equate them. That's the 2ax plus 3. That's the derivative for the part where x is greater or equal to 1. And then the derivative of the other half of the function is a constant 2. Now this is true when x equals 1. So we have this. And a equals. So skip some of the working just because we're running a bit behind on time from the technical issues earlier. And then b is just a plus 1. Okay. Any questions? Okay. So then this is pretty much the same thing. It writes it a bit more formally with the limit. Okay. Mean value theorem. So if we have some graph of a function f from a to b, let's say this value is fa, that one's fb, then the average gradient across here, so this here is fb minus fa, and then that part is b minus a. What the mean value theorem is saying is that the average gradient across these points is the same as the gradient of some point, sorry, the derivative of the slope at some point c of the function between those points. Now, sorry, this is a bad diagram, but does anyone have questions about this? Okay. Now, question 7. Assume that we have a differentiable function such that f dash x less than or equal to 1 for all x in R. Now we have a value of the function at x equals 2, and we want to show that fx greater or equal to x for all x less than or equal to 2. Now, let's just say that a equals that some value of x less than or equal to 2, and b equals 2, since we know what the value of the function is at that point. Now with these questions, we always have to select the a and b and the function, and we simply use the equation. And so we have f2 Okay. This is applying the mean value theorem. And we can do this because the function is differentiable. And now f dash x, that's going to be always less than or equal to 1. So actually we have this. Now simplifying, f2 is 2. Now if we think about the sign of 2 minus x, well, here we have x is always less than 2, and so 2 minus x, that's always going to be greater than 0. So we multiply through. And then if we rearrange this, we end up getting this. Any questions? Okay. Right, this is right, yeah, with the domain. So this is true for x smaller than or equal to 2. Okay. Next one you have is L'Hopital's rule. Okay, let's just move on to the next slide. Now, if we have f and g differentiable functions and a is a real number, then if we want to evaluate this limit, then we can try differentiating both sides as long as fx and gx either both go to 0 or both go to infinity as x approaches a. And well, if this limit exists, then it's going to be equal to this limit. So, when do we start? How are we going for time?
The room's free. It's like it's fine because I'm
Okay.
gonna go over by like half an hour or something.
Okay. Okay. Now we want to evaluate this limit using L'Hopital's rule. So actually, I'm going to give you guys probably a minute. So just, or maybe less, just think in your head, like how would you approach this question? And then not exactly doing any specific working out, but just like the general plan for applying L'Hopital's rule to this. Okay, does anyone want more thinking time? Okay, I'll take that as a no then. So, here it might look like at first that, well, applying L'Hopital's rule to this should be easy, right? We just check that, you know, they either both go to 0, both go to infinity, and then we differentiate the top and bottom, and then we get our limit. Actually, that's not quite the method, because if we differentiate the top and bottom, or differentiating the top, then, okay, note that we can write the numerator as this. So then using the chain rule, we get that. If we differentiate the bottom, we just get 1. And actually from here, it's not so clear how to proceed. Because if you think about h going to 0, then the numerator what happens to it? Well, h goes to 0. This 1 over h squared, that's going to get really big. So because of the negative sign, it's going to get really big and negative. And so that goes to 0. And then that also goes to 0. And now we have another indeterminate form. So, you might say, oh, use L'Hopital's rule again. But here, if you see, we used it once. Nothing changed that much except we increased the power of this. And I've just realized that it's also meant to be a 2 here. Or was it? No, it's on the top. But yeah, basically nothing changed much except we increased the power and we multiplied it by a constant. If we increase the power on the bottom from one use of L'Hopital's rule, then I'm not going to work through it, but if we use it again, the power is just going to increase. So actually, we require a different approach. Now, if we look at this expression, as h approaches 0, well, what happens to the top? Remember that this is just as then that approaches now because this h will go to 0, so the numerator will go to infinity. And this h here will go to 0, so that will go towards infinity, and e to the power of like a really large number that approaches infinity. And so that's an indeterminate form. We can use L'Hopital's rule for this because it's infinity over infinity. Okay. So differentiating this, or more clearly differentiating the top and bottom. This is what we get. And then if we simplify that, Now, as h approaches 0, then the numerator approaches 0. And the denominator, well, we see that we have this e to the power of 1 over h squared term. We've already established that that goes to infinity. So we have this. And now, this is just going to go to 0 because a small number divided by a really large number, that's going to approach at 0. Okay. Now we have this second part, which is determine whether the function is differentiable at x equals 0. Okay. Remember that the definition of the differentiability of a function at a point is whether this limit as I'll run out of space to write this, but as h approaches 0, if this limit exists. Okay. Now we want to find this for x equals 0. And we know back here from this definition, well, fx is 0. That's how it's defined. And fh over h, substituting h into the definition of the function at other points is going to give us so this limit, actually it's the same limit that we evaluated just now. And so that's going to be 0. And because the limit exists at x equals 0, then the function is differentiable at x equals 0. Okay. So any questions? Okay. In that case, here's basically the same working. In that case, we'll move on to the next thing. Now, this is where Chiang takes over.
Hello, I'm Chiang. I'll be taking over from Angela for the rest of the calculus session. And okay, we're behind a bit, so I'm going to try to do this bit faster than I usually would. I believe we will still run over time though, so like feel free to leave at any point before this ends. But I don't believe we'll be kicked out because I don't think this room is booked after us. So like we can probably go until like I guess like 2:20 or something. So anyway, let's just get straight into content then. So inverse functions, right? So one theorem that you guys should know is about whether a function has an inverse is that if f is a one-to-one function, or as some of you might know, injective, then we say that f has an inverse where the inverse of f will be a unique function, which we denote by f to the -1, with the property that with the property that f of f inverse of x. Okay, this is f of. Let me zoom out. With the property that f of f inverse of x will just give you back the original number, right? And same with the other direction, right? If you apply the inverse to a function output, you will just get the function back. And the range of our inverse will just be the original domain of f. So another theorem, the inverse function theorem that you guys should know is that if you have an open interval I, and if you guys recall, we just open intervals are like intervals of this form where you have two circular brackets rather than square brackets at the end. So if you have an interval, say a, b, and a function defined from that interval to the real numbers, and you have that f is differentiable with such that its derivative is never 0 for all inputs from your interval, then you know that f is 1-to-1 and or injective, and it will have an inverse function given by if we call it g. Well, from before we see that the its domain is going to be the range of f, and its range is going to be the domain. Sorry, g's domain is going to be the range of f, and g's range is going to be the domain of f, like the range and domain swap, because you kind of the inverse function takes you back from the function's outputs back to its inputs, essentially. And one extra thing is that g is differentiable at all points in the range, so all point in the range of f, so it's differentiable at all points in its domain, and the derivative of g is given by the formula g dash x equals 1 on f dash g of x for all x in range f. There is a little bit of a caveat to the second section, where sometimes you have that your f dash g of x is 0, and in that case g is technically g is not differentiable at that point if you do have a point x in the interval such that the derivative such that f dash of g of x is 0. So that's a little caveat to the second point, but the rest is true. And an alternative form for the inverse function theorem is that you can phrase it as in this form, where instead of writing g, you just have f dash f, you just replace it with f to the -1, denoting f inverse. So for a particular value of x, we have that the derivative of the inverse at that point is equal to 1 on f dash f inverse c. So any questions on this inverse function thing? No? Okay, good. So let's move on and do a couple of problems. So for example, question 9, if consider the function f from the interval 0 and 2 root pi to r defined by f of x equals x squared plus cosine x squared. Find all critical points of f and determine their nature. Explain why f is invertible. State the domain of f inverse x. And find f inverse of 5 pi on 2. And see where is f inverse differentiable. Right? So I guess we can get started with A. So find all critical points of f and determine their nature. So if you guys recall, the critical points of a function are going to be endpoints. Okay, endpoints. Stationary points. And points where the derivative doesn't exist. Okay, so let's go through them all. So for endpoints, we just have 2 root pi because the interval is open on the 0 hand side. So 0 is not in the interval. So the only endpoint we have is going to be 2 root pi. So let's check. To check for stationary points, we now consider the derivative of f. So we can just get the derivative by using like power and power rule for the x squared, and also chain rule to derive cosine x squared. The derivative of cosine is sine, and the derivative of x squared in it is 2x, so we just get minus 2x sine x squared. And we want to check when this we have our stationary points when this is 0. So we set this equal to 0 to find for stationary points, and we see that we can factor out a 2x. So we are getting 2x times, in brackets, 1 minus sine y. Ignore that too, hold on. Oops. I was thinking of something else. So we have 1 minus sine x squared, and we set this equal to 0. And first of all, you should note that x is always going to be positive. It's never going to be 0 because the function is not defined on that domain. So we can safely cancel out the 2x, well, divide by 2x because it's never going to be 0. And we get that the only stationary points are given by sine x squared equals 1. So that means x squared is going to be some is going to be like pi on 2, like 5 pi on 2, I think. 5 pi on 2, 9 pi on 2, and so on and so forth, and so on. But we also note that we have that x has to be between 0 and 2 root pi, just because it must be an input, like x must be on the interval. So that restricts x squared to be strictly bigger than 0 and strictly less than 4 pi. So 9 pi on 2 is going to be bigger than 4 pi, and anything that's negative is going to be less than 0. So the only solutions we have are x squared equals pi on 2 and x squared equals 5 pi on 2, which just gives that x equals root pi on 2 and root 5 pi on 2. And another thing I should say is that the derivative always exists on this interval, so we don't have any critical points of the third form where the derivative doesn't exist. So all of our, and so we will have critical points at x equals, let me scroll down a bit, x equals root pi on 2, x equals root 5 pi on 2, and x equals 2 root pi, because of course we can't forget to include endpoints. So any questions for part A? I'll take that as a no then. So, oh wait, and to find their nature, well, we will do the second derivative test. So the second derivative of this, f double dash x is going to be 2 minus, and then we use product rule, 2 sine squared x squared minus, like, I think 4 x squared not sine squared, sorry, just going to be sine x squared cos x squared. And well, okay, I'm not going to plug it in because it will take a lot of time, but like if you do substitute in these values, you will just find that when x equals root pi on 2, root 5 pi on 2, and 2 root pi, I believe when x equals root pi on 2, it's a point of inflection. When x equals root 5 pi on 2, it's a point of inflection. And that when x equals 2 root pi, you have a global maximum. So, yeah. Any questions regarding the second derivative test or determining? Another way you could determine the nature of the nature of these stationary points, or of these critical points, is by looking at the derivative around that. So if we approach the, like, for example, for root pi on 2, we see that as we, like, when x is less than root pi on 2, this whole thing is going to be, I believe, negative. And then after that, wait, no, sorry. This, note that 1 minus sine x squared is always going to be positive, and 2x is always going to be positive. So this derivative is always going to be non-negative. This could be 0, of course, which is what happens at stationary points. But essentially, that means the derivative, if we approach x equals root pi on 2 from the left-hand side, the derivative is always positive. And if we approach it from the right-hand side, the derivative is always positive. And that means that they are points of inflection. And what that essentially means on a graph is that, okay, if you have your points of inflection, like say here, here, and here, the function's going to look something like this. It's not going to look exactly like that, but whatnot. Another way you could do this is solving with Maple. So you could import the package student calculus and set f to be this, and then find the critical points using this. And note that Maple, you can't really specify open and closed intervals. So it gives you that the critical point includes 0 but does not include 2 root pi, which is incorrect because it's open on this end and closed on the other. So if you do use Maple, just watch out and you do use the critical points package, just watch out that you've included the correct endpoints. Moving on, Part B, explain why f is invertible, state the domain of f inverse, and find f inverse 5 pi on 2. Well, okay. From the nature of the points of, we have that all the stationary points are points of inflection, right? And that the derivative is always non-negative, right? So we get that, we have that the derivative is always non-negative, and when the derivative is 0, x is a point of inflection. That's enough to tell you that. So therefore, f is increasing on the interval, and also that means f is 1 to 1. 1 to 1. So if we scroll back up and go to our theorems, we see that if f is a 1-to-1 function, then the inverse will have to exist and it will be unique. So that tells us why f is invertible. And so the domain of f inverse is going to be the range of this function. So let's calculate the range. Since it's an increasing function, we can just look at the endpoints. So domain of f inverse given by open bracket f of 0, since it's the domain of f was open at 0, and close bracket on the other side, f of 2 root pi. And so if we just sub-plug it in, where we remember fx equals x squared plus cosine x squared, we get that the domain is going to be like 1 and 4 pi. 4 pi plus 1. And is that all for B? And find f inverse of 5 pi on 2. One way you could do it is I think using Maple with fsolve. Another way you could do it is to realize that you have that f of root, I think 5 pi on 2 is going to be root 5 pi on 2 is going to be equal to x squared, so root 5 pi on 2 squared, which is going to give you 5 pi on 2, plus cosine x squared, which is going to be 5 pi on 2. And if you remember anything about your trig functions, is that cosine is 0 when it's pi on 2 plus some multiple of pi. So this cosine term becomes 0. And so you get that f of root 5 pi on 2 is 5 pi on 2. So that means if we apply the inverse function to both sides, we get f inverse f of root 5 pi on 2 equals f inverse 5 pi on 2. So the inverse, so like since these functions are inverses, they cancel out. So you just get f inverse 5 pi on 2 equals root 5 pi on 2. And otherwise, if you couldn't spot this, don't worry, because like you can use Maple to like set or like f to be this function, and then f solve, and then put like, for I'm not going to write it up because it's kind of annoying to write Maple by hand, but you would put like f solve f equals like 5 pi on 2 in terms of within, and specify the range to be between 0 and 2 root pi, and then you'll again get root 5 pi on 2, and that will be your answer. Any questions for part B? Let me give you guys a bit of time to write that down. So I'm going to assume that's no questions for part B. So then I'll just move on to part C. So where is f inverse differentiable? Okay, from our inverse function theorem, we know that g is differentiable everywhere given by this formula, except when f dash g of x equals 0, right? So we know that our inverse sorry. Let me see if I have space. Yes. Oh wait, yes, you're right. Okay, that's actually smart. Okay, I'm stupid. I'm a little bit stupid. So f dash x differentiable except when f dash f inverse x equals 0. So we want to, we already calculated the zeros of f. So f dash x equals 0 when x equals a root pi on 2, root 5 pi on 2, root 9 pi on 2, and so on. So we want to find when the inverse is one of these. So like from part B, we know that or when x squared. And we note that from part B, we know that f inverse of like 5 pi on 2 is going to be root 5 pi on 2. And like if you just calculate the rest, you'll see that f inverse of like pi on 2 is going to be like root pi on 2, and so on and so forth. But you also need to note that x has to be in the domain of f inverse, which is 1, 4 pi plus 1. So like you can't have, I think, 9 pi plus 2 or 9. Oh wait, no. You have that it's differentiable everywhere on this domain, except it's differentiable on here, except when x equals root pi on 2, root 5 pi on 2, and so on and so forth. And the last one will be like root 4k plus 1 pi on 2. And you note that this has to be such that all of these have to be between 1 and 4 pi plus 1. So any questions on this? I'll just write part C here. It's okay. Okay, I guess I will move on to the next question, right? So, yeah, these are just, the solutions are just more formal ways of writing it up. So yeah, so like part B from the previous part, we know that like the derivative is always positive. So f is increasing in its domain and it's injective, yada, yada, yada. And again, like using the inverse function theorem, we have the same thing. And this only wrote two of this. Oh yeah, all solutions within the domain of f inverse. Oh, there should be more, but like, well, like the solutions are just like a more formal way of writing up what we had there, right? So moving on to curve sketching. So, okay, you guys have heard of like vertical and horizontal asymptotes before, right? So like a vertical asymptote is like, what the hell? It's gonna be like a dotted, like a line here such that the function like approaches it, but like never actually touches it. And a horizontal asymptote is like the same thing but horizontal, right? So oblique asymptotes are kind of like a general way of, a more general version of these asymptotes. So basically, they're like any lines, not just vertical and horizontal. And so like, for example, if I have like a function x plus 1 on x, it's gonna look like, I believe, this. And basically, you see that the function approaches the line, asymptote y equals x, but it never actually reaches it. And we can more formally define oblique asymptotes by saying like a straight line given by the equation y equals ax plus b is an oblique asymptote for a function f if as the limit of x approaches infinity or as x approaches negative infinity of f of x minus this function is 0. Basically saying these two lines, the function and this line here, get infinitely close together, right? So that's oblique asymptotes. It's a more general version of vertical and horizontal asymptotes. So for question 1, curve sketching, sketch y equals x squared plus 2. So y equals x, we want to sketch this function on x minus 2. And so the first thing we do is find the intercepts with the axes. So when x equals 0, y equals 2 on negative 2, so y equals negative 1. When y equals 0, we want x squared plus 2 to be 0, which isn't possible, so no solutions. So we only have an intercept when y equals negative 1. The next thing we do is find all asymptotes. So our vertical asymptote is going to be when asymptote is going to be when x equals 2, because then the bottom becomes 0, and then you have the 2 bits diverge off to infinity. And let's look for, we don't have a horizontal asymptote because like the two terms don't have the same, the polynomial on top doesn't have the same degree as the polynomial on the bottom, so no horizontal asymptotes. And oblique asymptotes, well, we can note, for oblique asymptotes, we can note that x squared plus 2 on x minus 2. The idea is to apply long division on this, polynomial long division on this. So we get like x squared. Oh, sorry, no, not x squared. Let me, x, I believe, plus 2, plus 6 on x minus 2. We can just find that through polynomial long division, as I said. So that means that we will have oblique asymptote x plus 2, well, y equals x plus 2. And the reason that is because as x gets really large or really positively large or really negatively large, the 6 on x minus 2 term essentially goes to 0. So the difference with that this function has with the line y equals x plus 2, the difference goes to 0 as x becomes large positively or large negatively. So we have an oblique asymptote here. The last thing we need to do is find turning points. So, well, find critical points, but like there will just be all turning points. So find critical points. So first of all, the derivative, we can use quotient rule. So we get that y dash is going to be the derivative of the top, 2x times the bottom, minus the derivative of the bottom, 1 times the derivative of the top, so divided by the bottom squared. Okay, so this is going to be 2x squared minus 4x minus x squared minus 2, and that's over x minus 2 squared, and we're going to have that this is x squared minus 4x minus 2 on x minus 2 squared. So the derivative doesn't exist when x equals negative 2, but we already noted that there was a vertical asymptote when x equals 2, so that's not a critical point. We don't have any endpoints, so we just want to find when this quadratic equals 0. And the way we do that is just by using the quadratic formula, since I don't see really any fast ways of doing it. So x equals 4 plus minus root 4 squared plus 8 on 2, which is going to be like 2 plus minus root 24 is like 2 root 6. So 2 plus minus root 6. And okay, I might not do the thing accurately as you should because we're a bit low on time, but like the main thing is to see that, okay, first draw in the axes, of course, and then draw in the asymptotes. So what the hell? So first draw in the asymptotes. So we have an asymptote at x equals 2, and another asymptote when y equals x plus 2. So we see that as x approaches infinity, the original function approaches infinity, so we have like something like this. And we see that when x is less than 2, it's going to be negative. So it's going to approach from here. Note that our y-intercept is at -1, and we don't have any x-intercept, so it never crosses the x-axis. But we have an asymptote here, and this point is -0, -1. We also should note our turning points are like 2 minus root 6 something, and our turning point here will be 2 plus root 6 something. You're supposed to just plug it into the original function to check, but that's essentially everything we have. So any questions on graphing? I'm going to assume that's a no. So like the main idea, find the intercepts, find the asymptotes, find critical points, and then use that to graph your function. Anyway, another thing we should find is, I should mention, is going over polar coordinates. So like if P is a point on a plane, Cartesian coordinates are just going to be Cartesian coordinates are going to be our regular XY coordinates. And but another way to view points on a plane is using polar coordinates, which is going to be r theta. And r is going to be the distance from the point to the origin, and theta is going to be the angle the origin, the vector to the origin, to the point from the origin makes with the positive x-axis count anti-clockwise. So for example, if I have a point here and I label it P, then it will have coordinate this. If this is R and this angle is theta, it's going to have coordinates R theta, right? So those are just a few polar coordinates. And you can convert from polar coordinates back into Cartesian coordinates just by setting x to be r cos theta and y equals r sine theta. And you can just see, like on the diagram, like if you just draw in these two lines, you see that this length is going to be r cosine, well, it's going to be like cosine 180 minus theta. But like, it's going to work out because like of trig laws. And this length here is going to be r sine theta. So that's the motivation behind converting it back. And yeah, so another question we can do with polar coordinates. Usually they won't ask you to graph polar coordinates. If they do, you can use Maple with the plots package and just put polar plot and so on and so forth. I think that was covered in the Maple workshop. But like, usually they don't ask you to draw polar graphs by hand, but they can ask for gradients of polar graphs. And the way you find the gradient, dy dx, is just by using chain rule. So for example, usually the method is dy dx is going to be dy d theta times d theta dx by chain rule. And you can get dy d theta by converting from polar coordinates back into Cartesian. And you can get, and then taking the derivative with respect to theta, and you can get d theta on dx by just inverting dx on d theta, right? Because that's the inverse. And so one example of this is like find the gradient of this curve where theta equals pi and 6. So if I convert back into Cartesian coordinates, I find that x is r cosine theta, so it will be 6 sine 2 theta cosine theta, and y will be r sine theta, 2 theta sine theta. So I'm going to say dx d theta, let that be, not let that, it's going to be like 12 cosine 2 theta cos theta minus 6 sine 2 theta sine theta just by product rule, dy d theta, this is going to be 12 cosine 2 theta sine theta minus plus 6 sine 2 theta cos theta. And so using chain rule here, well, we know that d theta on dx is going to be 1 on this, and we multiply that by dy d theta. So we know that dy dx in terms of theta is going to be the second function, 12 cos 2 theta sine theta plus 6 sine 2 theta cos theta all over 12 cosine 2 theta cos theta minus 6 sine 2 theta sine theta. And to just find, and then you just plug in theta equals pi on 6 to find out what it is. Right, so any questions? Actually, I don't think we'll have time. So I'll just move on to the first fundamental theorem of calculus, which says that if f is a continuous function on the closed interval ab, then we have a function big F from ab to r defined by fx equals the integral from a to x of little f t dt. And we know that it's continuous on ab, differentiable, and ab with derivative big F dash x equals our original function for all x in the open interval a and b. This basically just says that integration and derivatives are opposites. If you apply one then the other, then you'll just get the original function back. Or well, if you integrate after you derive, you'll be left with a constant term, but like you can choose that particular constant term to be such that you get the original function back. Theorem, the second fundamental theorem of calculus, says that if f is a continuous function on a and b, and big F is an antiderivative of f, so that just basically means that big F dash x equals fx, the definition of antiderivative, then the integral from a to b of little f t dt is going to be big F of b minus big F of a, right? So how can we apply this? So find d dx, integral 0 sinh x times cosine t on 1 root 1 plus t squared dt. So like, okay, we see that this function cosine t on root 1 plus t squared, that's kind of hard to find the antiderivative itself. You'll probably, I don't think there's a closed form, but you can certainly try. But the main idea is to recognize you have a ddx and an integration, a ddx and an integral. So you're going to want to use the first fundamental theorem of calculus. So what that tells us is that, like, say, let big F x equals integral from 0 to x of cosine t on root 1 plus t squared dt. Now, the second fundamental theorem of calculus tells us that integral of sinh x cos t on root 1 plus t squared dt is going to be big F of sinh x minus big F of 0, but okay, minus big F of 0. And then taking the derivative of both sides, d dx, I'm just going to like not rewrite that. We get, by chain rule, f dash sinh x, and the derivative of sinh x is cos x, because just remember your hyperbolic trig identities. The derivative of, well, f of 0 is a constant in terms of x, so it disappears. So that means we have that the left-hand side of this, the derivative of integral from 0 to sinh x of cosine t on root 1 plus t squared dt is going to be the derivative of the big F and sub in sinh x times cos x. But you know that the derivative of this by the first fundamental theorem of calculus is going to be f of x, right? So we get that this right-hand side will be little f of sinh x, cos x, and little f of x is just going to be what's inside, so cosine t on root 1 plus t squared. So this is going to be root cosine sinh x all over root 1 plus sinh squared x cos x. And if you remember your hyperbolic trig identities, you notice that root 1 plus sinh squared x and cos x are the same. So we get this is equal to cosine sinh x. Okay, I'll give you guys like a few seconds to write that down. I'm sorry. We had some technical issues at the beginning. Okay, so moving on to integration by parts. Well, integration by parts is just a formula where you have integral of u dv equals uv minus integral of v du, and you can derive this from product rule. I won't go over it since we don't have much time, but like let's just go through the question, right? So use integration by parts to evaluate integral from 0 to root 3 of arctan dx. So the way you're going to do it is like, okay, let me write up the integral first. Integral 0 root 3 tan inverse x dx, right? Tan inverse x is kind of an annoying function because, like, well, there's no really closed form solution to that. Oh wait, no, there is a closed form, but like you'll find it by integration by parts. So like one thing to keep in mind is that if you have an inverse function that you're integrating, usually you want to use integration by parts to diff the function, because you can find the derivative of inverse functions using our trick from before. If you recall from the inverse functions, like it's given by like the derivative of an inverse function, like you can express it in terms of the original function. So like Okay, let's do that. Sorry, right? So u is the term we diff. So let u equals arctan x, and let dv equals dx. So that, I should write let. So let, that means du is going to be, I'm just going to use the formula, 1 on root 1 plus x squared. So remember your inverse tan derivatives, and v is going to be equal to x. So that tells us that, let me zoom out actually so you guys can just look at it while I continue. So this integral is going to be uv evaluated at 0 and 3. So uv is going to be x tan inverse x evaluated at root 3 and 0 minus the integral of v du of v du is 1 on 1 plus x squared. So this whole thing, well, it becomes, okay, I think like inverse tan of root 3 is pi on 3, so it becomes like pi root 3 on 3, and when it's 0, when x is 0, x tan inverse x is 0, minus, and then if we evaluate this, we get like log absolute value of 1 plus x squared, half that actually, just by, like, you can u sub the bottom, because the diff of the bottom is 2x, and that 2x dx, so that cancels with this. So we want to evaluate this at root 3 and 0. So then we get that this is going to be pi root 3 on 3 minus half natural log of 4 minus half natural log of 0 is just going to be half natural log of 1, which is going to disappear. So we're left with that this is just pi root 3 on 3 minus, and you can simplify the log 4 into like 2 log 2, so to cancel out the half. Yeah. So yeah, the main idea behind this is to diff inverse functions using integration by parts if you are integrating an expression with an inverse function. Let's see. And then you can just get the rest easily. So another way you can sometimes use integration by parts is that sometimes when you're integrating by parts, you can return to the original expression, right? So what I mean by that is like, okay, if any of you remember like the classic integral of like e to the x sine x, you get it, you can express it as like half e to the x sine x plus half e to the x cos x plus c or something. And the way you do that is by integration by parts. But the way we do that is by, okay, I guess it's just easier to show directly. So like, suppose we have this integral, right? We are going to do the thing, okay, we're going to let u be sine log x, which makes du 1 on x cos log x by chain rule, and dv equals dx, which makes v equals x. So that means this is the integral of u dv. So we have that this is going to be uv, so x sine log x minus the integral of v du, and v is x. So we have x, v du is going to, there should be a dx after this. So v du is going to be x times 1 on x times cosine log x dx. So that's the 1 on x and x are going to cancel. So this is going to be cosine log x dx. And then now you see that we have something in a very similar form, right? So we're going to use integration by parts again. So like let u equals cos log x du equals negative 1 on x sine log x dx. Sorry for that. dv is going to be if we let dv be dx, we get v equals x. So integration by parts tells us that this second integral of cos log x is going to be uv, so x cos log x, minus integral of v du, and v du is, the x's are going to cancel, and the negative sign is going to cancel here, so we're just left with sine log x dx. But notice that this is our original integral, right? So like, if we let the original be I, we see that I equals x sine log x minus x cosine log x minus I, right? Because this is integral of sine log x dx. So that if we move I to this side and divide by 2, we just get the original integral is going to be half of what remains. So half x sine log x minus half x cos log x. Oh, and plus c, of course. Don't forget that, since it's an indefinite integral. Basically, integration by parts can be used like in a non-direct way like this. I think like there's also like the classic integral like e to the x sine x. Usually you see sine and cosine. You can use integration by parts to find this indirectly. But I might leave that as an exercise for you guys to do at home, perhaps, if you are looking for more problems. Other than that, moving on to the limit test. So this is basically seeing whether improper integrals converge or not. So if f and g are integrable functions that are non-negative on this interval a to infinity, and their limit as x approaches infinity of f of x on g of x equals L, where 0 is less than L less than infinity, basically the limit exists and is positive, either both of them converge or both of them diverge, right? So, I mean, the reason this is true is basically that f of x and g of x essentially grow like a similar amount, like they're in O of each other. So like like summing one should be like almost very similar to summing the other. So like the convergence is exactly, if one converges, the other must, and if one diverges, the other must. So the way we can use this is essentially by converting the inner expression of some nasty integral into something that's easier to integrate but grows the same amount, right? So determine whether the improper integral converges or diverges. So note that dx, we want to see if this converges or diverges, but like we can't really find the closed form expression of like the antiderivative of this very easily. So instead it will convert to a nicer function. So like we'll compare it to a different integral, right? So notice that this grows on the order about x to the 5 on 2, right? As x approaches infinity, which is like x to the negative 3 on 2, right? These two functions grow the same amount, right? Because as x gets really big, the x to the 5 matters much more than the x cubed plus 1, right? So these grow to around the same amount, and the way you formalize it is by saying like the limit as x approaches infinity of x on root x to the 5 plus x cubed plus 1 all over x to the negative 3 on 2 is just going to be 1, I believe. So that means by this limit comparison test, this integral right here converges if and only if the integral from 1 to infinity of 1 on x cubed on 2 converges, right? And okay, oh well, you can like evaluate this integral directly and get like it's like x or like 2/3 root x infinity and 1, and like this converges. Okay, this isn't like the formal proper way to do it. Like but one way you can see that this converges is that like the antiderivative of the inner expression is like 2/3 1 on root x, which and if you if x gets really large, it goes to 0, and when x equals 1, this is 2/3. So like this integral will always be so this integral will converge. But a better way to do it is to use the p-test. So recall that like the p-test tells us that the integral from 1 to infinity of the function x to the p dx converges if and only if p is like strictly less than -1. Right? And like, yeah, basically we see that in this case p is -3/2, which is less than -1, so this must converge. And by the limit comparison test, the original integral must also converge. Are we all good with that? Anyway, last few things to say. So log and exponentials, right? We can often use logs to simplify limits when we have exponentials in our limits, because since log is a continuous function, okay, I'll just, you can look at the solutions here. I won't write it up since we're kind of strapped for time. But like if you're asked to find the limit as x approaches 0 from the positive side of sine of x to the tan of x, you can take the log of, we can let y equals the limit, assuming it exists, and take the log of both sides. And the motivation behind taking the log of both sides is that log turns exponentiation into multiplication, which is much easier to work with limits. And also that log is a continuous function, so we can actually move the limit outside, right? Because if log wasn't continuous, then this move from this line to this line would not necessarily be valid. But log is continuous, so we can say this log y is the limit as x approaches 0 from above of log sine x to the tan x. We can drag the tan x out using log rules and see that when x approaches, we see that this goes to 0, but sine x goes to 0 as well, which means log x goes to -infinity, which means we have like 0 times -infinity, which is an indeterminate form, so we need to use L'Hopital's rule. And the way we do that is just by converting tan x into 1 on cot x, and then taking the derivative of both sides, right? And you can see here, like, okay, well, like, I'll just write the motivation behind the steps, but you can see the solutions, read the solutions. Tan x goes to 0 from above, log sine x goes to -infinity, so tan x times log x, log sine x is of indeterminate form, 0 times -infinity. And the way we convert we want to convert it either to be infinity over infinity or 0 on 0 to use L'Hopital's rule. So we just take 1 on cot, we just convert tan into 1 on cot x in order to use L'Hopital's rule. And then L'Hopital's rule tells us that we can take the derivative of the top and bottom and get the limit is going to be as x approaches 0 from above of cot x on negative cosecant squared x, which is going to be 0 because you can just sub it in now since these two are defined at 0 and non-zero at 0. And so since log y is 0, we can exponentiate both sides to get y equals 1. Yep. So if you encounter a limit of exponential form, you can log both sides. And of course, if you have a limit of like log form, you can either drag the limit in because it's continuous, or you can like exponentiate both sides since either the x is also continuous. Last few things, hyperbolic functions. Of course, like remember your hyperbolic function identities and how they're defined, right? Cosh x is half e to the x plus e to the negative x, and sinh x equals half e to the x minus e to the negative x. And you have your like identities like cosh, like the diff of this is sinh x, and the diff of this is like cosh x. So they form a cycle, and you see how that's related to the original sine and cosine functions, except the derivative of cosh x is not negative sinh x. Hold on, did I get it? No, yeah. You also have like the identities, of course, like sinh squared x. Wait, no, cosh squared x minus sinh x equals 1. And your double angles, right? Cosh A plus B is going to be like cosh A, cosh B minus, plus sinh A, sinh B. So like it resembles the cosine or summation angle formula. And same with sinh. It's of the same form, like it's going to be sinh A cosh B plus sinh B cosh A. And you can define hyperbolic tan of x as like sinh x on cosh x. And you have like very similar tan angle identities. And the reason we like to use hyperbolic functions is because is to use them in trig substitutions, right? Because like if you have like root x squared on minus 1 on the bottom, it turns out like you have that. It turns out if you like sub x to be sinh x or sinh u or sinh theta, the bottom turns out to be like well, in this case it's cosh theta. If you sub x equals cosine cosh theta in the bottom becomes cosh squared theta minus 1, which becomes sinh theta, which cancels with the derivative, right? If you didn't use hyperbolic trig, another way you could do this is by u subbing x equals secant theta, because of course secant squared theta equals tan theta, but then the top becomes like, so you get like integral sec squared theta over like tan theta times the derivative of secant is like sec theta tan theta, but then you get you get some really annoying secant integral which you need to use integration by parts to solve. But another way you could do this is of course like letting x equals cosh u, where dx on du equals sinh u, and since root x squared minus 1 equals sinh u, like this cancels with this, so you get that you just have the integral of cosh squared u du, and you can use this identity, which comes from the fact that cosh 2u equals cosh u plus u, and you can use your double angle, right? Cosh squared u plus sinh squared u, but sinh squared is just going to be cosh squared plus 1, so we get 2 cosh squared u minus 1, and then if we move this one over to the other side and divide both sides by 2, that's how we convert our cosh squared integral. It's very similar to your cosine and sine identities with trig. And so you get this integral, and then you can just evaluate it since the integral of cosh is going to be sinh, and you get this. However, yeah, and then you have to express u back in x, since we have an indefinite integral and we want everything to be in terms of x at the end. And we know that, we know sinh 2u equals 2 sinh u cosh u. You can again derive that from our angle formulas, but this again, you can also recognize that this is very similar to the double angle formula for sine, and you get sinh 2u equals this expression, so therefore you can sub it back. And of course u is, since cosh u equals x, u is the cosine cosh inverse of x, and you add c at the end since it's an indefinite integral. Sorry if that was a little fast and you didn't catch up on everything. You can of course rewatch the live streams after today, but like other than that, feel free to leave, and I hope you guys learned something today. So yay! Sorry if everything was a little fast. We were a little strapped for time since our setup at the beginning was not the best. Oh, yes.
Oh, yes, but I